So the next speaker is Rosalba Garcia Millan, and the title is Entropy Production of Non-Reciprocal Interaction. Please, Steph.
Thank you so much for inviting me. So I'm going to talk about entropy production of non-reciprocal interactions. Oopsie. Okay. Oh, yeah. So non-reciprocal interactions are present in many systems. One example is in bird flocking. So the Bishop model explains how this type of phenomena can arise by birds aligning their velocities with their neighbors. But there are other models of bird flocking where birds interact with only some of their neighbors. And so, for example, excuse me, some birds are able only to see some of their neighbors. This is because of this vision cone. And so this interaction is non-reciprocal because there is this directionality. There is this other example of particles or Einstein-Uhlenbeck particles that are coupled with some, sorry, just 1 second. Yeah, Einstein-Uhlenbeck particles that may be coupled with springs. And in this, well, this system is generalized in this paper by Loos and Clapp. And so you see that the dynamics of particles are coupled, but they are coupled in a way that the effect is not equal to all of the particles involved in these couplings. And so, for example, if we look at these green and orange particles, the green particle is coupled to the orange one, but not the other way around. And that gives rise to a non-reciprocal interaction. So this can be generalized. And the system can be described by these Langevin equations. And so you see that this matrix here is giving the couplings on where the diagonal terms are giving the stiffness of each harmonic potential. And whenever this matrix is asymmetric, those interactions are non-reciprocal. There is an external force, and there's also a Gaussian white noise. So in general, this system is out of equilibrium, except for a particular choice of parameters. So there's one choice of parameters where even though the interactions may be non-reciprocal, the system is still at equilibrium. So what I'm going to show today is a model I've been looking into. This model involves non-reciprocal interactions between two different species. And I'm going to show how to describe this model using a Doi-Peliti field theory. And I will also talk about the entropy production of this system. So in this project, there are two main motivations. One is to understand how these non-reciprocal interactions are related to non-equilibrium systems. And we also want to learn how to implement these pairwise interactions in a field theory. Okay, so in the model of dog and sheep, there are these two species. One is called the dog, and the other ones are the sheep. Within each species of particles behave the same way. They have a self-propulsion velocity and a diffusion constant. And on top of that, particles interact only if they belong to different species. So dogs interact with sheep interact with dogs, but dogs don't interact with other dogs, and sheep don't interact with other sheep. The type of interactions are mediated by pair potential, and this potential may be attractive or repulsive. So here's an example where black dots are representing sheep and the red cross represents the dog. And the type of potential that is governing the interactions is such that the dog is attracted to the sheep and the sheep are repelled by the dog. And so what you can see is that the dog will run towards wherever sheep end up accumulating. And then as it does so, the sheep run away. And so behind the dog, there's this trail of empty space. And here is another example of a much larger system the diffusion constants are very small, and essentially these particles are very localized. And all the interesting things and stuff that's happening in the system is due to these interactions between the dog and the sheep. So if we want to describe this system mathematically, we can do so by writing this system of overdamped Langevin equations. So here X, there is one dog and there are n sheep. X represents the position of the dog, and Y1 and so on, they represent the position of the sheep. Then this U cross or U dot, they represent the velocity of each of these species. Here this V are the potential, the pairwise potentials, and on top of that there is this thermal white noise. You can see that the interactions happen between the dog and the rest of particles, here by this sum, and here because each of these particles only interacts with the dog. Okay, so this Langevin equation can be written into a Fokker-Planck equation form. Here the P is the joint probability distribution of finding the particles at X, Y1, and so on. And here you can see there are these diffusion terms, and then there are these force terms which involve the potentials and the self-propulsions. So I said I would talk about the field theory of this system. So we worked on the duality field theory of this system. This involves, because there are two species of particles, involves two types of fields. So for the dog, we chose phi, and for the sheep, we chose psi. And because this is a duality field theory, it involves creation and annihilation fields. So the non-tilted fields are annihilation fields, and the tilted fields are Doi-shifted creation fields. And these need to be understood in a similar way as in the quantum mechanics ladder operators of creation and annihilation. So from the Fokker-Planck equation, we can write down the action functional, and we split this into two parts. The first part is governing the Gaussian dynamics. So you can see there's the time derivative, the diffusion, and the self-propulsion for each of the two species. And then in the perturbation part, we write the interactions between the two species. And there are these two terms, essentially, and these two mediate the effect of the interaction on each species separately. So in the first time, we have the effect of the interaction on the field phi due to the presence of the field psi, and the other way around in the second term. So in this system, we are now reducing it to one dimension. It's going to be on the ring, so it's a periodic system, and we need to demand that the potentials are bound. And in under these assumptions, we can write down these Fourier transforms of the fields and the potentials, and write down the action functional is in Fourier space. And by doing so, what we get are these two types of elements. On the one hand, we get the Baire propagators. So here, these are the Feynman diagrams. These represent on the top, it's the Baire propagator for a phi field. Here we have the Baire propagator of a psi field. And on the right, we can see the Baire propagator in Fourier space, so which corresponds to a drift diffusive type of particle. And then the interaction couplings are given by this symbol. So here, what we can see is the effect of the interaction on the sheep, on the dog, due to the presence of the sheep, and the other way around. It involves some of the Fourier nodes, the K's, and some delta functions. So the first thing we wanted to calculate was the 2-point correlation function. So this observable is written like that. Initially, the system is initialized with, we start only with 2 particles, so it's going to be 1 dog and 1 sheep, and they are placed at different positions, x naught, y naught. And at a later time, we want to measure what's the probability that we find a dog at position x and a sheep at position y. And to calculate this observable, what we do is a perturbation expansion about the non-interacting case. So the 0th order term doesn't involve interactions. And as we go higher in orders, in this perturbation expansion, we have the expansion to first order in the potential, and well, to second order and so on. So these calculations are quite messy, but we could calculate this 2-point correlation function in the limit, in the stationary limit. And in that case, we could see that this 2-point correlation function can be mapped to the distribution of the position of a particle in an external periodic potential. And that distribution is known. It's given by this expression. And well, so in the case that the particles have no drift, or they have the same drift, then this distribution of the distances between the 2 particles is of the Boltzmann type. So to illustrate things, I chose this potential, which has a shape of a cos function. And now what we are going to tune is the amplitude of this cos function. So if this A is positive, we have a shape like this, and the potential is repulsive. And if the amplitude is negative, then the potential is attractive. So here are some examples. We now take no drift, so drifts are 0, and here are the diffusion constants. And so if, for example, now we choose that the amplitudes of both potentials are repulsive, we have a type of dynamics like this. So you can see the 2 particles repel each other, and they tend to stay away as much as possible. In the case where both potentials are attractive, have both a negative amplitude, then the particles tend to stay as close as possible. They are also subject to fluctuations, so the system is, I mean, they are not always on top of each other. And then there's a third case where one particle has an attractive potential. In this case, it's the red cross. It is attracted to the black dot, and the black dot is repelled by the other particles, so it tends to stay away. And every now and then they meet and they may swap their direction of motion, but they generate this non-equilibrium steady state when they start running around the ring. Okay, here. So well, so for the case where there is only 1 dog and 1 sheep, we can calculate this 2-point correlation function exactly. And if we compare it to the simulations, the agreement is very good. And so what happens if both potentials are repulsive is that particles tend to stay away as far as possible. And therefore, you can see this shape of the distribution of the distances. Whereas if both are attractive, then the distances tend to be very, very small. And in the case where one particle is chasing the other one and that other one is running away, what we see is that this profile tends to be flat. And in this case, these amplitudes are very close to each other, but if they were exactly the same with opposite sign, then this would be exactly a uniform distribution. So other observables that are interesting is, for example, the mean square distance. So here on the horizontal axis is the amplitude of one of the potentials of the 2 particles. And on the vertical axis is the amplitude of the other potential. And so here, if we look at the mean square distance for when both potentials are attractive, the mean square distance is the smallest, and as we get more and more repulsive potentials, the mean square distance increases. And if we look at the velocity-velocity correlations, what we see is that there is, well, if both potentials are either attractive or repulsive, the velocities tend to anti-correlate. That's because they are either facing each other or running away from each other. Whereas if one particle is chasing the other one, there is an effective, well, the velocities are positively correlated. And this is interesting because this alignment appears effectively, although in the model there is no explicit alignment interactions. So we looked at the entropy production of this system, and this is the general expression for the entropy production of a jump Markov process. And so here we need to take this limit of tau to 0. Tau is an interval of time, and we are integrating or summing over all possible states or pairs of states in the system. And then we have this expression. So P is the probability to be in state X, and W is the transition probability to go from state X to state Y in an interval of time. So we have this bracket and then the logarithm of these two quantities. In this system, it's quite easy to write down the entropy production when there are only two particles. So this is the distribution of the distant interparticle distance. And then we have this bracket squared, and this gives us, well, this is always either 0 or positive. And whenever it's 0, this gives us the condition for detailed balance, which is very similar to the one found in the Lowe's and Clapp paper. So for the choice of potentials that I showed earlier, here in this, it's a bit like a diagonal. Here in this black or dark region is where detailed balance is satisfied. And as we move away from this line, what we get are higher and higher values of the entropy production. So that's interesting because this is telling us in this, for this choice of potentials, the case that gives greater entropy production is that where one particle is chasing the other one and that other one is running away. So that's the case of the largest lack of reciprocity. Okay, and then we also wanted to know what happens if we introduce more and more particles to this system. So we're going to have one dog and n sheep. And so this, well, we looked at this 2-point correlation function as we increase the number of sheep in the system. And this 2-point correlation function is between the dog and one of the sheep. So here, for example, we have that all potentials are attractive. And what we see is that as we increase the number of sheep, the distance between the dog and one of the sheep tends to decrease. And so here, similarly, what we see is that so here, all potentials are repulsive. And what we see is that as we increase the number of sheep, particles or the distance tends to be larger and larger. And for these other two cases where there's one attractive potential and one repulsive, what we see is that this 2-point correlation function tends to be flatter and flatter and flatter. So if we write down the expression for the entropy production in the same way as I showed earlier, now what we need to deal with is the n+1 joint probability distribution. That in principle is not available, but okay, so this expression still simplifies because we can integrate some of the degrees of freedom. And so in the end, this entropy production depends on the 2-point and 3-point correlation functions. So now it's a matter for to find a way to estimate these 2-point and 3-point correlation functions using the field theory. Again, we can find the condition for detailed balance. So this is the same condition as we found before. in the case of one dog and one sheep. And this, it makes sense because if as we increase the number of sheep, or let's say as we add a new particle to the system, if the system is at equilibrium and the new particle satisfies the detail balance condition, the system is still going to be at equilibrium.
You've spent 20 minutes. Please summarize the talk shortly.
Yes, thank you. So this takes me to the conclusions. The first conclusion is that the lack of reciprocity breaks time reversal symmetry, and there except some choice of parameters. In the case that, in the case where the lack of reciprocity is largest, the entropy production is also largest. And and then we want to extend this this system to many particles, and we want to understand how the entropy production increases or changes under this many particles. And finally, this is an example where we can implement pairwise interactions in a perturbative expansion. And our goal and intention is to look at a similar type of system, but instead of having passive motion, we want to have active motion. So, for example, random tumble particles or ABPs. This work was done with Zulu Zhang, and we acknowledge Gunnar Pusner. They're both at Imperial College. And well, thank you so much for listening.